Dear students, continuing with our lecture series on stereochemistry, this is our sixth lecture and second lecture on asymmetric synthesis. In the last lecture, we have discussed about some basic concepts of asymmetric synthesis, and in this particular lecture, we will see the details about selectivity in asymmetric synthesis, and this selectivity can be achieved by selecting appropriate substrates or reagents or solvents or reaction conditions. In this case, we will discuss mainly these three types of activities, that is chemoselectivity, regioselectivity, and stereoselectivity. First is chemoselectivity. Chemoselectivity is basically uh, uh, an ability to distinguish between two distinct functional groups which are present in the substrate. So the reaction will be taking place only one of these two functional groups and not on both of these functional groups. So because of that, the asymmetric synthesis will identify the group involved in the reaction. So we can say that chemoselective reaction is that reaction where the preference is given to one of the functional groups present when a reagent react with a bifunctional molecule. Now we can have different examples of the chemoselectivity. For example, if you see this molecule, para-nitrobenzoic acid, now we are having a carboxylic group also and nitro group also. And if we are to undertake reduction of this group, either nitro or carboxylic acid, when it is done in presence of palladium on charcoal in the alkaline medium, then basically it has been seen that reduction of only carboxylic acid group take place and nitro group is not affected. So that means out of the two functional groups, this reagent has selected the reaction to take place at this functional group and not at the nitro functional group. So that means this reagent is a chemoselective reagent and this reaction is a chemoselective reaction, and the process is called as chemoselectivity. Otherwise, if this is a reducing agent, either it should reduce nitro group or nitro or carboxylic acid, both groups they should be reduced to amino and hydroxyl functional groups respectively. Similarly, another example is selective reduction of carbonyl groups. So for example, if you see this molecule, this is having this carbonyl function group as well as this carbonyl function group. Now, if you see the structure of the molecule, this carbonyl group is different from this carbonyl group because here this is an alpha beta unsaturated carbonyl compound. And when reduction of this carbonyl compound is done with sodium borohydride, it has been found that it reduces only this carbonyl group and not the alpha beta unsaturated carbonyl group. So that means sodium borohydride is a selective reagent for reduction of these type of carbonyl functional groups which are not having any alpha beta unsaturation present. Whereas if we use this reagent borane, if hydrogenation oxidation of this molecule is done, then the reduction of this ketone, which is alpha beta unsaturated ketone, take place, and this isolated ketone is not affected. So basically we can say that this reagent is chemoselective for the reduction of this carbonyl compound, and sodium borohydride is chemoselective for reduction of this carbonyl. So such reactions, they are called as chemoselective reaction. And similarly, if we are having, say, this type of uh, compound, now this again is having two carbonyl groups, but one carbonyl is aldehydic carbonyl and other carbonyl is ketonic carbonyl. And if the reduction of this carbonyl compound is done with sodium borohydride in methanol in presence of CeCl3, then reduction of the ketone will take place and aldehydic group is not affected. Whereas if the same reaction is done with same reagents except CeCl3, instead of CeCl3 we are using dichloromethane, then reduction of aldehydic group will take place and the corresponding alcohol will be formed. So again, this is the third example for chemoselectivity for such type of reactions. The next is regioselectivity. So regioselectivity indicates about part or the site in the molecule where the reaction takes place in that group. So basically, regio means the region or the direction. So this regioselective has come from the Latin word regionum, which means direction. So if there is a possibility of formation of a product at two places in a given compound, then if reaction take place at one region selectively, then that type of reaction is known as regioselective reaction, and the process is known as regioselectivity. So we can say that it is the selectivity between two positions in a system with similar reactivity, or where there is a possibility of reaction on two sides or both the sides. For example, in case of epoxides, so now if you see this epoxide, 2-benzoyl oxirane, if you see this carbon and this carbon, they have different environment. This carbon is attached to a benzyl group, whereas this is unsubstituted carbon, where there are two hydrogens attached. And when if a reduction of this followed by hydrolysis is done, that means automatically ring opening of this epoxide ring will take place to give you alcohols as the product. And now the we know that in case of reducing agent, the attacking reagent here is the hydride ion in case of lithium aluminum hydride. So hydride ion will attack out of these two carbons that carbon which is less hindered side to form the alcohol. So that is why the attack of the hydride will take place at this carbon and not this carbon. So that means the reagent hydride has selected this region. So that is why this is called as a regioselective formation of 1-phenyl propane 2. Similarly, we can take another example, that is in case of benzophenone and uracil. If a Paterno-Bucci reaction take place, we know the oxytanes, four-membered ring containing oxygens, they can be formed, and the reaction is known as Paterno-Bucci reaction. Now, the addition of this carbonyl to this alkene can take place in two ways. Either this oxygen can join this carbon, or this oxygen can join this carbon and this carbon will join this carbon. So there is a possibility of formation of two regioisomers. So this is the first regioisomer where this oxygen will get attached to this carbon and this carbon will get attached to this carbon and we will get this type of product. And second regioisomer is when opposite happen, that this carbon gets joined to this carbon and this oxygen gets joined to this carbon. So addition is inverted in this case and we will get this type of regioisomer. So we can see that the formation of this isomer is almost 2.5 times more than this isomer. So this again is an example of regioselective reaction where one of the isomer is formed in more amounts in comparison to the other. Then a few other examples are Michael addition reactions where we see that in some cases addition is 1,2 addition whereas in other cases it is 1,4 addition. For example, in case of alpha beta unsaturated carbonyl compounds, if the nucleophile attacks this carbonyl, then we will be having 1,2 addition, whereas if the nucleophile attacks this beta carbon, then 1,4 addition takes place. So these two modes they can be exemplified very easily. So if we differentiate between say aldehydic group and ketonic group towards nucleophilic addition reaction, it has been seen that in case of aldehydes, in majority of these addition reactions, 1,2 addition will take place. For example, if we are having this propane to enal, this is an aldehydic functional group. If we add this HCN and the reaction is taking place under alkaline conditions, so nucleophilic addition of cyano group at this carbonyl system will take place and addition is an 1,2 addition reaction. And similarly, if the corresponding ketone is there, then the nucleophilic addition reaction take place at 1,4 addition. So by this way you can see that we can differentiate between 1,2 addition and 1,4 addition. So these these two type of reactions, they are examples of regioselective reactions. Then regioselectivity, as we have seen in earlier example also in cleavage of epoxides. So again, for example, if we are having this epoxide 2,2-dimethyloxidane, and even if we change the reaction conditions, then also behavior of this reagent changes towards the region at which the reaction will take place. For example, when the reaction is under acidic condition in presence of methanol in acidic medium, then the attack will take place at a weaker bond which will be attacked by the nucleophile. And nucleophile here is our solvent, that is methanol, and attack will be taking place at more hindered side of the molecule and we will get this as the product. Whereas if the same reaction is run under basic medium instead of acidic medium, then the attack of the nucleophile will take place at the less hindered side. So sterically less hindered carbon will undergo bimolecular nucleophilic substitution reaction to give us this type of product. So this is a beautiful example of regioselective cleavage in case of epoxide. Similarly, in case of 4+2 Diels-Alder reaction, if we see this type of 1,3-diene, when it adds to these types of enes, then there is a possibility of formation of two types of product. Either this carbonyl is towards the this oxygen, and a coordination complex is formed between these two oxygen, and because of this addition of this carbon to this place and this carbon to this place take place, and we will get this as the product. And other is opposite to this, the this carbon adds to this place and this carbon adds to this place, and we will get this type of product. Again, we can see that one of the anisomer or one of the isomer is formed in more amounts, and again this is an example of regioselective reaction. Then is stereoselectivity. Stereoselectivity is, as you know, if some reaction take place, for example addition of say bromine to cyclohexane, the attack in the first step, one bromide will add to the alkene, and we will get a bromonium ion, and then the second bromine as the nucleophile will attack this carbon either from this side or from this side, and there is a possibility of formation of two isomers. And if the reaction take place in such a way that both the isomers they are formed in same amount, then we say racemic mixture is formed. But if the possibility of attack of the nucleophile from one side is more in comparison to the other, then one isomer or one stereoisomer will be formed in more amount. So such type of reactions where uh, formation of the products take place in a stereoselective manner, so as one stereoisomer is formed in more amount or is formed selectively over the other stereoisomer, then such type of reactions they are called as stereoselective reactions, and the process is called as stereoselectivity. So as far as details about stereoisomers in terms of ionomers or diastereomers, and details of their conceptual facts is concerned, we have already discussed these in the first lecture, that is asymmetric synthesis basic concepts, where I have already explained that how stereoselectivity can lead to the formation of enantiomers and diastereomers, and this stereoselectivity leads to enantioselectivity or diastereo selectivity, depending upon whether the product is a diastereomer or an enantiomer that is produced selectively. So a few more examples of stereoselectivity. For example, Sharpless oxidation is one example where an enantioselective process. For example, in this case, this is an allylic alcohol, 2E but2E 1-ol. When this is reacted with titanium isopropoxide, tetraisopropoxide, in presence of this optically active reagent diethyl tartrate, uh, this can lead to the formation of these two enantiomers, and you can see that out of these two, one enantiomer is formed in 98% amount, and this enantiomer is formed in 2% amount. So that means the reaction is a stereoselective reaction, because one of the enantiomer is formed in more amount in comparison to the other amount. Another example is Sharpless asymmetric dihydroxylation in case of this biphenyl tetrahydropiphenyl when Dihydroxylation is done under these conditions in presence of optically active reagents. Then there is a possibility of formation of four stereomers from this biophenol. So these out of these four stereomers, it has been found that only one stereoisomer is formed in with 98% enantiomeric access, and again this is an example of stereo selectivity. The third example is dehydrohalogenation of 2-iodobutane, and similarly, if this is treated under basic condition in presence of a strong base like potassium tetrabutaoxide in DMSO, then dehydrohalogenation will take place. Either this can take place this way or this way. So there is a possibility of formation of these diastereoselective products, and you can see that one of the diastereoisomer is formed in more amount, that is in 60% in comparison to the other. So that is why this again is an example of stereoselective process. The next example is in case of alpha beta unsaturated ketones. If these are reacted with this Gilman's reagent dimethyl cuprolithium, and we know that under these conditions this will undergo alkylation reactions. So these two alkylated diastereomers, they can be formed either trans or cis, and it has been found that trans product is formed in predominant amount, that is 98%, whereas cis is formed only in 2% amount. So this again is an example of diastereo selectivity. Another example is this S optically active aldehyde. If this is reacted with trimethylsilothioazole to form this SS diastereomer, only this anti diastereomer is formed. The syn diastereomer, that is SR diastereomer, that is formed only in small amount, whereas this is formed in 92%. And the formation of this diastereomer in major amount again gives us an idea that this reaction again is an example of stereoselective reaction, where one of the stereoisomer is formed in more amount as compared to the other stereoisomer. So these are the references which have been used for preparing this lecture. Thank you very much.